Okay, so now we move on and we want to see another sorting algorithm. It is merge sort. And this is the recursive sorting algorithm. And before now, and we have seen the bubble sort, we have seen the insertion sort, but those are the basic sorting algorithm. There's no insertion, no recursion inside. But for this one, this is special. Well, the first thing I want to remind you is, well, considering the general layout of a recursion, and the first thing in the function definition, we are looking for the base cases. But in this one, in this code, we don't have base cases. And on the line 3 and line 4, we see recursive steps. So what are the base case or the base cases? I would say it's kind of hidden. If you see the line 1 is if left smaller than the right, and then we'll go inside and we will do the recursion. But if left is not greater, if the left is not smaller than right, and then we do nothing, right? So this part, if left is greater or equal to right, and then we do nothing, and that is a base case. And since for the base case we are doing nothing, so it's not in the definition. And by looking at this code, and you may find it is a little bit strange. And I would say the base case is hidden. So and you don't see the base case part. Okay, and for the merge sort, the general thinking or the general design of the merge sort is we want to break a big list into small parts, and eventually we want to break them into all of the one values. And after doing that, we want to merge the two values together into a sorted small list. Okay, so let me say it again. First, we want to break all the values into one value sublist. And then the next part, we want to merge the small list together into a bigger merged sorted list. And then we are going to keep on doing so, and eventually after we merge, we will merge everything together into a big sorted list. And this is the thinking. So let's see how the code is implemented. Well, A is the list we are gonna sort. And then for the left and the right, well, that is the upper bound and the lower bound of the portion of the list we are sorting. Okay, and if the left is smaller than the right, and what we are going to do is we will grab the middle value, and that is the left plus the right, and then divided by 2. And then for this part, this looks like a square bracket, but this means a floor division. So we divide, and then we go by the lower value. Okay, and then after that, we have two recursive calls, merge sort and the same list, but then we define the boundary of the sorting to be the left to the q, which is the middle value, and then another merge sort from the q plus 1 to the right, and then that's the upper half. If we are sorting the entire list at the very beginning, and by doing the line 3 and line 4, we are breaking a big list into small parts, and then we are recursively sorting the two small sublists. Okay, so this is the plan. And eventually, after we have done the two recursive calls, here is another step. We want to merge the A, right, Q, and left. So after they are all sorted, we want to put them together again. So let's see this example. We are sorting 7 values, and the first part, the first part is we want to do a break it into 2 parts. And how do we do that? And if you see this line of the code, that is the left, right, and then divided by 2. But if we are following the style of our textbook, and then we have index 1, 2, 3, 4, 5, 6, 7, if we are using the 1 base index, right? So the left will be 1, the right will be 7. So what is the middle value? The middle value will be 4. So if we have the merge sort like this, and the first one is we want to do a merge sort A, comma 1 to 7 if we are doing one based indexing. And then we will break it into two parts. And what are those two parts? So we will have, I'm going to do MS A 1, 4. So that is one of them. From 1 to 4, so 4 values. And another one will be merge sort, and then A 5, 7. So we have A, and then from 5 to 7, so 3 values. So when we are doing a split, and if we are off by 1, the left one will grab one more value than the right one. Okay, this is my observation. And if I want to do a split again, because the left is 1 and the right is 4 in this case, so left is still smaller than right, so a further split. And after that, okay, it should be here. So after that, we should have 1, 2, 2. And then another one, merge sort 3 to 4. So those two will be a further split for this one, right? So if we continue doing the split, say I want to do another split for this one, and then I will have merge sort 1, 1 and merge sort 2, 2. So after I have go that far, and what am I doing here? Merge sort A 1, 1. What is that? That is, I'm just merge sort this value, right? So if this is just only one value in a sublist, and then I want to sort it, well, there's nothing to sort because there's only one value. So eventually, when we go all the way down, following the recursive tree structure, we will end up with sorting all those 7 values as individual sublists. So eventually, what we are doing is we are sorting just a 10, and then we are sorting just a 5, and 7, 6, 1, 4, and 8. Well, this is eventually when we break down the recursive recursive tree structure to the leaves, and we will see this. And after that, so 10, it's already sorted, nothing to do. 5, 7, 6, nothing to do because they are the only values. And what's the next step? Remember, we want to do this part. We want to do the merge. We are combining the sorted sublists together into one. So we are going to combine those two. So 10 and 5, if we combine them, it will be like this, right? 10 and 5. And then 7 and 6, they combine together will be 7. Oops, my bad. It should be 5, 10 instead of 10, 5. And 6, 7. Okay, and then 1, 4, that is 1, 4, and then 8 will be itself. Okay, this is one step of the merging. We are merging all of the leaves together into 2 item lists. And then we are going to do another merge. So we merge those two, and what are they? It will be 5, 6, 7, 10, right? So we merge those two, we got 5, 6, 7, 10, and how about we burn those two? That will be 1, 4, 8. Okay, so we haven't done yet, but by doing the merging, and eventually we are getting closer to the final merged list. Okay, so let's do one more merging. So one more merging, we will have 1, 4, 5, 6, 7, 8, and 10. Well, that is the merging. So eventually we merge all the sorted sublists together into one final sorted list. So it seems that that's pretty cool, right? Well, but there's one thing we didn't talk. That is, what is the cost of doing the merging? Okay, so let's just use this one for example. Okay, I'm going to delete this one. And how do we merge those two and finally get a merge final list? How do you start this process? Okay, so think about that. If you're coding Python and you have two sorted sublists already, or just sorted small list already, and then you want to put them together into a one final sorted list, how are you going to do that? So this is my plan. Okay, so I'm going to create a cursor called I. Oops, you don't have to capitalize that for me. And I also have another cursor as J. Okay, I create a I, a J as two cursors. At the beginning, I stops at the first list, the beginning of the first list, and J is at the beginning of the second list. And also, I want to create a empty list. So, and my algorithm will be, I want to grab a value from I. I want to grab another value from J. I want to do a comparison. Whichever is smaller goes into this list. Okay, if you're running this algorithm, the first thing will be J, right? So J is 1, and then I'm going to move 1 down. And after that, I want to move the cursor down by 1, 2, because J has already touched 1. 1 is put into the final list. Now I want to move J to the next value. And then I do another comparison. I and J, which one is smaller? And I find that J is smaller again, so 4 goes here. And then I want to move the J cursor down by 1 again. Okay, after that, I value and J value do another comparison, but this time I value is smaller, so I'm going to move 5 down. And then I want to move I want to move I down by 1. So I is at 6 and J is at 8. And eventually, by using the trick of the I and J as two cursors, and I can put all the values into the sorted list together. Okay. So this is my process, or this is my algorithm to merge those two sorted lists. Okay, so my question is, what is the big CITA? What is the CITA just for this merging algorithm? And my observation is, no matter how many values we are going to sort, well, in this case, this is 4 plus 7, 4 plus 3, 7 values. Well, we are touching those 7 values once and only once. So either we touch that with the I cursor or we touch it with the J cursor. But my observation is we will touch each of the value only once. Okay, so this will give me a linear algorithm. So that is a CITA N. Okay, so after that, let's see the merge sort again. So let's see the merge sort again, and we want to put together all the effort to sort n value list. Okay, so for this part, the first line, we are doing a comparison. This comparison can be done in constant time, of course, and this one, the second line, is also in constant time. Okay, so if the Tn of the merge sort, the cost of the merge sort is Tn, and then what we are going to do on the line 3 and line 4 will be, we are splitting the list into 2. And then we are doing the same merge sort. However, the input size of the line 3 and line 4 recursive calls will be n divided by 2. So do we know the Tn? No, we don't. But one thing we know is if the Tn is the cost to sort n values, and then the Tn divided by 2 will be the cost to sort half of the list, right? So the line 3 and line 4 will be Tn divided by 2 and Tn divided by 2. And eventually for line 5, as we discussed, line 5 is a linear algorithm, so that is a CITA N. So let's put everything together. So for this part, we have we have the theta and one constant time, and 2tn divided by 2, and then one linear time. Okay, but what do we miss? How about the base case? So for the base case, we check this line of the code, and the left and the right, they are the same value. And then we do nothing. We just do one check, right? So for the base case, if we hit the line 1 and line 1 is a false, we have nothing to do, and that is a constant time algorithm if we reach the base case. Okay, so let's put all the information together. So Tn is going to be a constant time, or theta 1 when n is 1. And otherwise, it will be 2Tn divided by 2, and then plus a theta n when n is greater than 1. Okay, that Tn is a little bit weird. Remember, our goal is we want to have a polynomial as a Tn, but now what is that? The definition of the Tn is more like a conditional structure, and plus, well, when n is greater than 1, it is also a recursive definition of the Tn. And my observation is I don't like that. Why? Because I want to start from a polynomial Tn to really have a serious analysis about the big O, big omega, and big theta, right? And look at what we have got. We got a recursive definition of the Tn, and this is not this is not the part we can start to do the big O and big omega and big theta. So I'm gonna stop here, and the next lecture I'm gonna show you how we can start from the recursive definition of the Tn, and we want to break it down and we get a polynomial version of the Tn. Okay, so I'm gonna stop here.